how does the helium affect the environment?
Good question. So helium doesn't really have any effect on the environment because, it looks like a lot of helium because it's like a really big balloon. But in fact, once the balloon is released and the helium can sort of disperse, it's just going to slowly mix in with the rest of the environment.
Well, I had a question. You had said that the landing velocity for your telescope was around 38 miles an hour, correct?
Around 35, yeah, roughly.
Oh, okay. Well, usually that stuff is pretty sensitive. Is that slow enough for it, or I don't know? It just seems a little fast, like it'd smash when it hits the ground.
It's a really good question. So it is the velocity. That is the situation that we have to deal with, and it's not ideal. But you'll be amazed, actually, that there really wasn't much damage to the experiment. I'll go back. So looking at this picture here, it landed on its back, and so there were a couple electronics instruments right here, and they were like buried in the sand, like they were dead, like just put them in the trash, like crushed. It's not like you could open it up and, keep a few things. And then also these little feet, there's like these little welded structures. They bear a lot of the brunt of the landing, and it was specifically the back feet. Like the telescope came down on its back and then boom, fell over. So especially these back feet were really bent, and so we had to trash them. But like this table, which is made out of just aluminum I-beam, totally survived. This guy, some of these beams survived. In the end, we decided to redesign it, so we replaced a lot of it, but we even reused some of these parts from this structure. Our mirrors were totally fine. And all the electronics that were mounted sort of in this area here were totally fine. The carnage you see is a lot of the foam and the aluminized mylar. It's like a party balloon material. And you can see before launch here, it's all this shiny stuff is just foam with the aluminized mylar, the party balloon material, and really thin struts of aluminum, like little L angle. And that was just decimated. But we knew that would happen, and it's relatively cheap to make. So it's something you keep in mind when you design the telescope, that this is going to happen. And in fact, like we have like these structures sticking out here called quills, and we had a little roll bar, like you might see on the top of a Jeep or a truck. We had a little roll bar around our mirror. You sort of do the best you can.
Okay. To do this same experiment, is it something about the magnetic field down there that while you're going down there?
Oh, cool. Good question. So the magnetic field isn't important for what we're doing, although there are experiments that target Antarctica because they're looking at cosmic rays or certain particles that get funneled by the Earth's magnetic field down to the South Pole. But there are a couple advantages to working in Antarctica. When you launch your experiment, somebody mentioned like you don't necessarily want to be right next to the ocean because, if the wind takes you slightly to an unexpected location right after launch, you could end up in the ocean. And that's true even in the middle of the flight. Ideally, you'd want to stay over land the whole time. But, of course, they launch experiments, say, from Sweden as well, near the North Pole, and they drift over to Canada, and then they have to come down before they get over Russia. So that kind of shortens the flight, whereas from Antarctica, there's something called circumpolar winds. And these winds just run around the pole. So if you launch from McMurdo Station, which is actually not at the South Pole, but I don't even know. I probably should know, maybe, say, hundreds of miles away from the pole. That's my order of magnitude guess. The experiment just drifts right around the pole, and it'll make multiple passes around the pole. So it's like a convenient way of keeping the experiment over land, but allowing it to stay up for a really, really long time. And it can stay up for, 30, 40 days. We only have enough cryogens, enough liquid nitrogen and helium to stay up for about 14 days observing. And of course, NASA might keep us up there a little longer and only cut us down when we're in a convenient place to land. But we'll probably only be observing for a maximum of 14 days. That's one reason. Another reason is power. So we got to power all these electronics. They require about 2,000 watts. What are some ways you could get power to your electronics?
You have solar.
Solar, exactly. And in the summer, you've heard about the land of the midnight sun, maybe. My dad's from Norway in the northern hemisphere. That's where the sun stays up, all summer long. Same thing happens in the southern hemisphere during their summer. So you have 24-hour, 7 days a week solar power when you're that close to either of the poles. And, for our flight from New Mexico, we didn't fly solar panels because they would have also been smashed like everything else, and solar panels are super expensive. But we just used batteries because it was a short flight. But batteries are pretty heavy, and to get enough battery capacity to power our whole instrument was going to be impossible. We would have been over the weight limit of what NASA allows, so we have to use solar. So that's another reason why working near the poles is convenient.
What kind of classes did you take?
Good question. So I did an astronomy bachelor's, so I took physics at the beginning. And one important thing is I think no matter what science you study, it's really good to start in your main science major classes right at the beginning. So you might think like, well, I'll get to college, I'll see how it goes. And you can do that. If you need a year or semester to like get on your feet and get oriented, that's fine. But if you're going to do a serious science major, you got to really pack it in to 4 years. There's a lot of classes to take, and it's you have to take one before the other. So you can't just like take them all your junior, senior year. So it's good to get started early. I took physics and math pretty much every semester until my senior year. And in my senior year, I only took one physics class and no math. And I didn't take a lot of really advanced math, but you need some basic. You need higher level calculus and something called differential equations and linear algebra for physics. And then I took astronomy every, maybe not every semester, but almost every semester I took an astronomy class.